Ferroelectric Liquid Crystal Display (FLCD) is a display technology based on the ferroelectric properties of chiral smectic liquid crystals. It has been proposed in 1980 by Clark and Lagerwall as direct-view displays. The FLCD could not displace the LCDs based on nematic liquid crystals using the twisted nematic field effect or in-plane switching. Today, the FLCD is not used as direct-view display but in microdisplays based on liquid crystal on silicon devices. Used in LCoS, the dot pitch of such displays can be as low as 8 micrometers, giving a very high resolution display on a small area. To produce color and grayscale, time multiplexing is used, exploiting the sub-millisecond switching time. These find applications in 3D head-mounted displays, HMD, image insertion in surgical microscopes and electronic viewfinders where direct-view LCDs fail to provide more than 600 pixels per inch resolution. Ferroelectric LCoS find commercial use also in structured illumination in 3D metrology and super-resolution microscopy. Working of ferroelectric liquid crystals. Ferroelectric liquid crystals are chiral smectic liquid crystals that have a layered order. Within the layer, the liquid crystal molecules, called mesogenes, are tilted away from the layer normal 90 degrees, forming a so-called smectic liquid crystal. Chiral behavior is introduced by inserting a symmetric carbon atom into the mesogenic molecule, termed now smectic C**. The asterisk denotes the chirality. The chirality causes a smectic layer to exhibit a permanent spontaneous polarization at right angle to the tilt plane, giving rise to the term ferroelectric. In an unconstrained system, a helical twist in the structure lowers the energy of the structure, i.e., the tilt direction changes from layer to layer by some degree. In other words, the azimuthal direction in which the molecules tilt away from the layer normal will differ slightly from one layer to the next. Therefore, the overall polarization of an unconstrained smectic C** phase will be zero. Typically, the FLCDs are built with cell gaps less than 2 micrometers for stable molecular alignment. In this constraint system, the interaction between the alignment layers and the smectic C** liquid crystal suppress the helical superstructure. Proper ferroelectricity now forms in domains. The spontaneous polarization of the smectic C** layer interacts with the electric field applied to the electrodes. Depending on the direction of the electric field, the mesogenes are titled either to left or the right side of the layer normal. This in turn results in opaque or transparent state when used in combination with crossed polarizers as in LCD. Properties and uses. Very thin layer, less than 2 micrometers thick, produce a 90 degrees polarization twist. High-density LCoS displays with small display areas can be produced. Switching time is less than 50 microseconds. High frame rate video displays are possible. Polarization effect is bistable. Can be used for low frame rate displays that can run on very low power. This property can help build display with non-volatile memory with the advantage that the memory can be changed easily. In-plane switching provides reduced viewing angle dependence of contrast and color. Some commercial products utilize FLCD. High switching allows building optical switches and shutters in printer heads.